Lines in space are something that we're pretty familiar with in 2 dimensions, but we want to talk about it a little bit in 3D. But to refresh ourselves in 2 dimensions, we want to take a look at something called the point-slope form of a line. Now, a lot of us are more used to the slope-intercept, y equals mx plus b. But this is an alternate form that says that if we're through a point x0, y0, and you have a slope which can be defined as b over a, so notice in this case a is non-zero, then we can rewrite the values of x and y. We can write them sort of like as functions of t, and we can say that x equals x0 plus a times t, and y equals y0 plus b times t. Now, the reason why we might want to do that is that then we can drive the line completely upon t. So if I set up some sort of maybe I was writing a computer program or something like that, I can define these functions, fill in every number except for t, and I could almost have like a slider, and I could slide t and it would slide up and down, the locations for x and y would slide up and down the line. So notice that when we plug in 0 for t, these vanish and we get that x equals that point on the line. So we can be reasonably confident that we've constructed it correctly because we can always get just the point, that x0, y0 point from the point slope form. So realistically, we can take the slope, m equals b over a, and we can think of that more like a direction. So you remember, you think of it as rise over run, but if you think of it as terms of direction, you can almost think of it like a vector, right? You go up so many on the b and you go out so many on the a. So you have a direction line instead of a slope. You can think of it like that. The reason we want to do that is because in 3 dimensions, this idea generalizes really well. We can't really set up an equation like this in 3D because z would end up being a function of x and y, and there are some restrictions that make that a little more difficult than you might expect, because there's this interesting coupling that could happen. So a lot of times it's easier just to write stuff in terms of parameterization. So if I have some point x0, y0, z0, and I have some sort of direction vector, some sort of trajectory for how it behaves, then I can write the locations of x, y, and z in terms of, if you think of it, this is a point plus t times this vector. So another way that it's sometimes written, I didn't think to write this, but you can say that the xyz location is the initial location plus the vector times time, right? So I multiply the direction times some sort of t. Notice I said time here. It doesn't have to be time, but a lot of times that's just that's the reason we want to do that. We want to say at this time I'm in this location, at this time I'm in this location. So some v times t, and then you add that to the initial point. So this is almost like a shift. Think of like in 2 dimensions where we have that y-intercept is shifted. And so you kind of have a y equals mx plus b form, if you think about it like that. So anyway, this parameterized form allows us to think about the vector kind of this way. And what we have also, and this, we don't use this that often, but if none of those elements are 0, what we can do is we can solve each one of them for t. So we subtract this term and then divide by that one, and you get what are called symmetric equations. And these tell you fundamentally how x, y, and z relate to each other. This isn't used as often in sort of a real world scenario. You're much more likely to see this type of stuff, but the course material does include this, so we want to talk about that. And we're going to do some examples as time comes on.